In this video, we'll talk about how to bias a circuit with a transistor and analyze such circuits in order to obtain the operating point of the transistor amplifier. The simplest type of biasing that is applied to transistor circuits is the DC biasing. Biasing establishes the operating point or cue point for proper linear operation of the transistor circuit. If the circuit is not correctly biased, the amplifier circuit based on transistors can either go into saturation or cutoff when an input signal is applied. Typically, the input signal is a sinusoidal signal. In the figure, you see the symbol for an amplifier. It is a triangle tilted to the right. The input is represented by a line at the base of the triangle, while the output is represented by a line at the tip of the triangle. In the first figure, you will see a properly amplified signal biased correctly with a DC signal. The amplitude of the output signal is greater than the input signal. However, you will also notice that the output is 180 degrees out of phase with the input. We'll get to that later. In the second figure to the right, you see the same output signal with larger amplitude than the input signal, but with a portion of the signal clamped. The amplifier is biased incorrectly and is operating in the cutoff region. In the third figure at the bottom, we have the same output signal, again with a portion of the signal clamped. The amplifier is again biased incorrectly and is saturated. The figure shows the transistor amplifier biased with 3 DC bias signal. The top circuit is the lower DC bias generating a base current of 200 microamperes. The middle current is the higher DC bias generating a base current of 300 microamperes. The bottom circuit has the highest DC bias generating a base current of 400 microamperes. Since the DC beta is 100, the collector currents are 20 milliamperes, 30 milliamperes, and 40 milliamperes respectively. For the top circuit, the operating voltage is at VCE equals 5.6 volts. For the middle circuit, VCE equals 3.4 volts. And for the bottom circuit, VCE equals 1.2 volts. I hope you still remember how to solve for these values. Briefly, you obtain the base current by applying a voltage VBB and then dividing the difference of VBB and VBE, which is equal to 0.7 volts, by RB, which in this case is 10 kiloohms. Then you can determine collector current from the DC beta parameter. Once you have it, subtract the product of the collector resistor and the collector current, which is the collector voltage, from VCC, which is 10 volts in this case, to get VCE. You can watch the earlier videos on transistors to refresh your memory before you proceed. These operating points are called cue points and has coordinates of VCE and IC. The cue points follow the DC load line, which we already determined in the previous lessons. Again, the x-intercept of the load line corresponds to VCC and is called the cutoff point, while the y-intercept of the load line corresponding to IC sat is called the saturation point. The cutoff point is determined when VCE is modeled as an open switch across the emitter-collector terminal, while the saturation point is determined when VCE is modeled as a closed switch across the emitter-collector terminal. As you can see from the figure, the cue point follows the load line and determines the correct operating point of the transistor. If the transistor is properly biased, then the input signal is neither cut off or saturated. Here, the transistor is biased at VCE equals 3.4 volts. To achieve this, VBB equals 3.7 volts, which then gives us IB equals 300 microamperes. From the DC beta, we get the collector current to be 30 milliamperes. From the collector current, the operating point is then at VCE equals 3.4 volts. The input signal is coupled in series with the DC signal as shown. In the graph, the input signal is the red sinusoidal curve. The amplitude of the input current is 100 microamperes, with the middle value at 300 microamperes. At the collector terminal, the amplitude then becomes 10 milliamperes with the middle value at 30 milliamperes. The amplification is then determined by how the input signal is sort of refracted by the DC load line. Thus, the output voltage has an amplitude of about 1.2 volts, with the middle value at the Q point of 3.4 volts. Notice that the signal is also shifted by 180 degrees. We'll get to that soon. These figures depict what happens if the Q point is not selected correctly. If the Q point is closer to VCE equals 0, then the amplified signal is in saturation. If the Q point is closer to VCE equals VCC, then the amplified signal is in cutoff. Finally, even if the Q point is optimal, but the input signal is too large, then the transistor is driven into both saturation and cutoff. How then do we determine the Q point? In the given circuit, we can determine the Q point by first solving for the base current, and then the collector current, and then the collector emitter voltage. The Q point will then be the collector emitter voltage VCE and the collector current IC. To determine the load line, we need to draw a line from the x-intercept, which is the cutoff voltage equal to VCE equals VCC, to the y-intercept given by IC saturation. In the previous type of biasing transistor circuits, we considered two voltage sources to amplify the signal. In this circuit that we are now going to learn, there's only one voltage source, connected to both the base and collector terminals. The source voltage is VCC. The base terminal is biased by means of a voltage divider circuit using resistors R1 and R2. The figure shows how the currents flow through the circuit. Since R2 and RE are parallel, current goes through both resistors from the ground. The current through RE goes to the base terminal and the collector terminal, as we already know, and is consistent with the previous type of biasing. The circuit is typically designed such that the base current is much smaller than the current through R2. This becomes straightforward to analyze the voltage divided circuit since we can neglect the loading effect of the base current. The current through R1 then is just equal to I2. If this is the case, then we call the voltage divider to be a stiff voltage divider because the base voltage is relatively independent of different transistors and temperature effects. We can solve for the base voltage using the voltage divider equation as shown. Once we've determined the base voltage, we can solve for the emitter voltage, VE. The emitter current is then obtained next. We know that the emitter current and the collector current are approximately the same, especially since the base current is quite small. At this point, we've already determined one coordinate of the Q point. After determining IC, we can then solve for VC. This is given by the difference between VCC and the voltage drop across RC. Finally, we obtain the second coordinate of the Q point, VCE, from VC and VE. In this problem, we'll try to determine the Q point from the given circuit. Applying what we've learned from the previous slides, we obtain the following values for the Q point. In the given circuit, the voltage divider resistors are R1 and R2, equal to 10 kiloohms and 5.6 kiloohms respectively. VCC is 10 volts. The collector resistance is 1 kiloohm and the emitter resistance is 560 ohms. The DC beta parameter is 100. We first solve for the base voltage, which is given by the voltage divider equation, R2 over R1 plus R2 times VCC. Plugging in the known values, we get 3.59 volts for the base voltage. Now that we know the base voltage, we subtract VBE from the base voltage. VBE is just the voltage across the base emitter junction, which is 0.7 volts. This gives us the emitter voltage equal to 2.89 volts. After knowing VE, we divide it by RE to get the emitter current. The emitter current is then computed to be 5.16 milliamperes. And since the emitter current are is approximately equal to the collector current, then the collector current is also 5.16 milliamperes. Now, from here, we already have one of the coordinates of the Q point. To solve for the collector voltage, we take the difference between VCC and the voltage across the uh, collector resistor, which is ICRC. VC then is equal to 4.84 volts. Now VCE is the difference between VC minus VE. Note that the collector voltage is measured with respect to ground. So we have to subtract VE from VC to get VCE. This gives us VCE equals 1.95 volts. Thus the Q point is at VCE equal to 1.95 volts and IC equals 5.16 milliamperes. How do we design the circuit such that the base current is small and negligible compared to the current through R2? The figure shows what the resistance looks like at the base of that transistor. We call this the input base resistance. This includes whatever internal resistances are present in the transistor. The input base resistance is defined as the base voltage VB divided by the base current IB. Since IB is related to IE through the DC beta parameter, then the input base resistance is just equal to DC beta times VB divided by IE. We see that whatever internal resistance present in the transistor is sort of captured by the DC beta parameter. If this input base resistance is greater than or equal to 10 times the resistor R2, then we have a stiff voltage divider, and we can be assured that there is no loading of the voltage divider due to the transistor. Otherwise, we consider R2 and the input base resistance as parallel resistors, so that the base voltage is given in terms of these two parallel resistors, as shown in the equation for the non-stiff voltage divider. Let's take a closer look at the non-stiff voltage divider and examine the loading effects of the transistor to the voltage divider circuit using Thevenin's theorem. To determine the equivalent Thevenin circuit that biases the transistor, we redraw the voltage divider circuit as shown in B, where everything in the shaded area needs to be Thevenized. The Thevenin voltage is straightforward and is just the voltage divider circuit. To get the Thevenin resistance, we need to short the source VCC to ground. We see that the equivalent Thevenin resistance is just the equivalent parallel resistance of R1 and R2. We now redraw the shaded region to its equivalent Thevenin equivalent circuit in C. We then obtain Kirchhoff's voltage rule. Using Kirchhoff's voltage rule, the equation relating the Thevenin voltage, the voltage across the Thevenin resistor, VBE, and the voltage across the emitter resistor to be equal to 0. If we replace the voltage across the Thevenin resistor with IB and RTH, and the voltage across the emitter resistor with IE and RE, and then solve for IE, we get the given equation. Notice that if the Thevenin resistance divided by DC beta is small compared to the emitter resistance, then we end up with the previous result for IE for the stiff voltage divider. I hope that you've learned a few things about biasing transistor circuits for amplifier applications. The DC biasing and the voltage divider bias are two of the most common types of biasing used in amplifier circuits. There are actually 4 more types: the emitter bias, the base bias, the emitter feedback bias, and the collector feedback bias. I would like to encourage you to read about these 4 other types of biasing. While they are not so common as the voltage divider circuit, they are also typically used depending on some applications, and recognition of such type of biasing will be important when analyzing electrical circuits. Furthermore, I would like to encourage you to also read about biasing PNP transistors and figure out the differences and similarities with biasing NPN transistors. In the next video, we'll talk about transistor amplification, focusing solely on the voltage divider circuit.